Okay, students, sorry we took so much time today to get set up. Um, and as a result, I think what we'll do is dismiss early today if we can. Anybody against dismissing early? No, raise your. I saw one guy over here. He was faking me out. Psych. Uh, did anybody hear about that? Uh, no, the rocket that blew up at Cape Canaveral. SpaceX did. No, it's unmanned, and nobody. And I read on WFTV.com that there was nobody on the pad itself when it blew, but apparently it was pretty violent. All right, well, we'll try to learn about that. One thing, while Darianne is up here, I want to make a mention. She's been tweeting class notes and also your questions and my answers. You were doing that Tuesday, right? Okay, and Darian's going to be doing that, a few other things this semester as we speak in lectures, so you can actually flip up your Twitter and look at my Twitter feed, and it'll actually be Darian on the Brainwave 777X Twitter feed. But what I would like you to do is, if you feel that, looking at that either now or later, you can go back and look at it later. I would like you to let either me or Darian know verbally or in a message through the inbox system in web courses. Yeah, Dr. B, I like the tweets. It's helping me because, and then tell me how it's helpful. Or if you don't like it that much, tell me, Dr. B, they would be much better if, and then tell me, what they can be improved by. Okay, now that I'm asking Darian to just do kind of a skeleton version, not deluxe notes, but I want it to be a parallel to what you are doing. And in addition, you basically have verbatim notes in the YouTube of each lecture. So between what you do, what Darian is doing, and Caroline in the second lecture, and YouTube, somewhere in between there, you're going to be able to get everything wrapped around. And what that means is that in lecture, you can listen to me blabbing my big mouth up here for an hour, a lot more, and instead of furiously trying to take down notes and stuff. Okay, you can raise your head up and look. All right, thanks, Darian. So Darian's going to be doing that today. Also, the iClicker registration appears to be working. I have over half the class registered now. If you've got your iClicker and you haven't registered yet, and it's not working, try it again. It seems to be working. And there's a big ginormous thread in discussions about different techniques. And I've been keeping an eye on it. I synchronized it before class. If we dismiss early today and you want to double check to see if you're on the roster, you can come up after class and I'll activate. I'll just comb through the roster. One more thing. We're going to be doing an iClicker question today, a verbal iClicker question. And you're going to need to click in a number. And so when you get your clicker, or when we get to that point in the lecture, I'll ask you the question verbally. It'll be on the screen as well, but it won't be in the form of a multiple choice or anything like that. And then I'll tell you to click in your numbers. And by the way, I had a couple students text me, or not text me, but message me in web courses. Dr. B, I've been clicking. I got Go Nitro and everything, but I'm still not registered up. And that is correct. It is possible to not be registered, but yet to get Go Nitro. Now, if you're in class and you're not registered, I'll be able to hear your clicker as long as it's got good batteries. Okay, I just won't know who it is. Every time you send a click, whether it's a letter or a number or anything else, it first sends me the serial number of the device. It's designed to do that. Very simple, Morse code, a bunch of dots and dashes, I guess, ones and zeros. And it identifies itself and then tells me what it's sending. But I don't know what a given serial number is until you register. Now, over half the class is registered, so I know who's clicking what. But if you are in class and you haven't registered, you can still do it. So don't be deceived. If you get Go Nitro, that doesn't mean you're registered. Being registered is what means you're registered. Okay? And the reason they do that is this system is used in a lot of different settings where they don't really care the name of the person. A big room of people, they want to see, it's called anonymous polling. They don't really need to know who it is. But for us, it's part of your grade, so I definitely need to know that it's you. All right? Now, I want to give you another little tip. Every semester I try to get this going. And I really, really like the, I see your question. I'll get to you in a second. I really, really like the discussion so far. They've been really active. And I encourage you, come down, have a seat. No problem. Just come on down anywhere you want. If you come late to class, don't worry. I don't get too ticked off. Maybe about 0.01%. But anyways, discussions have been going good. So when you're in discussions, what I want you to do is type in a discussion title that's really specific. And so in other words, don't just say, help me, or homework, okay? That's because it's not going to help someone efficiently know what you're trying to ask about, okay? So make it very specific like this one, why was Galileo's third state of motion so important? Okay, and so something like, question or notes is, it's nice, but it's not very descriptive. So try to remember to do that. Also, click the allowed threaded replies box, if you will, and that'll keep the discussion semi-organized, and therefore helpful. And you can see who's replying to whom, instead of just a big ball of mayhem that, you can, if you don't want it to be a helpful thread, then don't make it like that. But it'll help everybody if you do that. Also, click the allow liking box, and that way people can give you the thumbs up or whatever the symbol is. All right. Now, questions about clicking and discussions over here. With the specs. You mean the bonus points? Yeah, that's right. The question was, if you've already gotten some of those bonus points, which for everybody that was registered up until about 2 o'clock yesterday, about 1 o'clock, I posted bonus points for Tuesday, Thursday, and Tuesday last week. Okay, if you weren't registered by 1 o'clock, you didn't get them. But if you registered at 1:05 and it's on the roster now, you'll get a bonus point for today, and you'll get a bonus point. Well, Tuesday next week is the official start. Okay, so this is the last bonus point day. So hopefully it's going to be quite a number of you. And yes, that does signify, because that's the only way I can post any points at all in web courses. If I know that your serial number is connected to your NID. And that's what the registration method does. So it behooves you to get in there and try it again. And if you're having trouble, go through that discussion thread. It's got a lot of tips in there, and hopefully that'll get you sorted out. Raise your hand if you know that you are registered. All right, so that's a good bunch of yous. All right, the rest of yous, if you know it hasn't worked, then try it again. If you think it's worked, check to see if you have bonus points. I'll probably put up another bunch tonight. Early iClicker bonus points. All right. Question.
I registered, and I did the question, but I didn't get any points. So I'm assuming that it didn't work.
Yeah. If you think you registered and you didn't get any points after yesterday, just try it again. See. And you know what? It's just like this. Did you guys hear about that thing up in Greenville, South Carolina? Those clowns, the scary clowns. Yeah. There's supposedly some prevert scary clown up there trying to lure little kids into the woods. I don't know. It is horrible, and it's also but it might not even be true. It might be, it might have happened once, and now it's, like a lot of these things, But anyways, I have no rational explanation for what. I'm still. I have no rational explanation for this clicking fiasco. All right, let's keep going. Last time we were talking about how to numerically structure in the manner that Galileo has set forth as a requirement the state of motion between a few hypothetical points. And we talked about different paths, the linked segments, straight line segment, one straight line segment, as a crow flies, and then a robot, that's the segmented path. And then this, the curved path, that's more like what a human or an animal would do between point A and point B. And we talked about, what we need to actually describe the motion. And we're going to go into this in a little bit more detail. The positions and distances in meters. The times and the elapsed times in seconds, between point A and point B. The directions, we didn't really talk about the directions a whole lot, but we will this morning. The speed at each time, and we didn't really put that all together. We kind of did some homework last night with distance calculations and with speed calculations, some basic ones. And we're going to go into more detail in this morning and into these 4 items of how you describe the state of motion, because it's pretty important. Now, here's one of the homework problems. This guy that walks into a door, stick figure, and I want to review this one. And I know a few of you got tripped up on it, at least for the first time or two. Julie, right? Yeah. Morgan, close. Close. I was close. She came up to me and said, "I'm Morgan in your morning class." And she's the one that told me about the SpaceX. And I'm trying to remember your guys' names, Erica and everybody. And I'm going to remember. So far, I got 2, 1.5. I kind of blew. Morgan, and I know your last name too. Anyways, I'm going to try to get your names down. So, anyways, let's look at this problem. It was basically given some temporal and spatial coordinates in this problem, anyways. Calculate the change in the x position and the change in the time position, delta t. And then from those, calculate the average speed. And here's a screen grab of the actual problem. And then enter the numeric part of your answer to the nearest 0.1 meters per second. Now, when you're doing homework, I want you to know that in a problem like this, I'll always tell you how to round off, all right, to the nearest 0.1 meters per second in this case. Or if I want a little bit more precision, the nearest 0.01. Or I might say the nearest whole number of degrees Celsius scale or something like that. I'll always tell you how to round off. Also, when you're doing these in homework, you have 4 different attempts, the Web Courses Canvas system gives you on your next attempt a different number. Now in this one, I believe the number that changes, it can be all 4 numbers, but I think on this one it's the T2. Time, the clock reading at event 2, I think that's the one that changes. So you might have 0.6, 0.8, or some other number. Okay, so when you're doing these calculation problems, make sure to read carefully and don't recycle your numbers. Recycle your strategy if you want, but don't recycle the numbers because they can change. All right, so now for this particular instance, my delta x, that's calculated this way. X later minus x earlier, x2 minus x1 in this case. 0.00 meters, according to the given information, minus a negative 2.45 meters. Now, subtraction of a negative, if you recall from 7th grade math class, subtraction of a negative is the same as addition of a positive. So 0 plus 2.45 is 2.45 meters. So there's your delta x. Now that's one of the calculations that you use to get speed or velocity. And it's based on 2 measurements. 2 position measurements gives you 1 delta x. Question? Okay. All right, so let me park that up here to the right. All right, here's the next thing that you've got to do, delta t. And that again is t final minus t initial. Later minus earlier, always. That's the order. And so in this case, it's T2 minus T1. And this one's a little bit easier to work with. 0.8 seconds minus 0.00 seconds. So that's 0.8 seconds. That's your delta T. And let me park that off over to the right. And now you put them together in a quotient to get your average speed. Here it is, 2.45 in the numerator, 2.45 meters. And then in the denominator, 0.8 seconds. Whoa! Anybody see an error? What error? And you're smiling. Like you're smiling. Yeah, Dr. V made an error. What do you see? Miles per second? Wrong. Meters per second. Yeah, Dr. B forgot to put meters per second here. Ooh, Dr. B napping. Anyways, go ahead and put in 3.0625 meters per second. That's what it's supposed to be. And that's a Dr. B typo. I mean, you can see it right here. Meters per second. 2.45 meters in the numerator, seconds in the denominator. And then over here, 3.0625 seconds, and that's a typo. All right, so now you type in the number, and here I got it right, 3.1. You got to round, and that's why I always tell you to round off carefully. All right. Now, this also shows you another little mystery. One of the scary clowns of Canvas, that it always puts in zeros. I typed in 3.1, and then Canvas added out those 3 extra zeros. Nobody that I know knows why they do that or how to turn that off. And there's a lot of things in web courses that unfortunately are like that. Anyway, so there's your answer. And remember, don't pay. If you don't type those zeros in, don't worry about it. You type in what I ask you to, and ignore those extra zeros in there, and then you'll get the right answer. Question?
We don't have to type in meters per second.
No, it says in the first part, it always says type in the numeric part. So that means just the numbers. Okay? So some computer systems, not web courses, but other websites, you can type in, meters per second. They show you how to do that. But I usually want to just concentrate on the numbers. And I'll always say that. I mean, if you go back and look at the actual problem, here it says down here, enter the numeric part of your answer down here at the bottom to the nearest 0.01. E.g., and I'll always give you an example. E.g., if your answer is 12.39 meters per second, then here's what you type in, just 12.4. Right? So I always try to include that. You know, I'll always ask you the calculation, do this calculation, and then I'll have a little paragraph like this. Okay, so, you know, and on exams the same, I'll tell you. Unless it's a multiple choice. If it's a multiple choice calculation that you have to do, a simple calculation for which the answer is in multiple choice, then I mean, you know, then you just got to spot it. But otherwise, that's it. All right, so let's go through here again. All right, here's the calculation. My typo. Okay. All right, so I want to look a little bit more carefully at this curved path. And so let's talk about these positions and distances and stuff on this curved path. And if you think about it, a curved path is more complex than a straight line path. And a straight line path is a certain distance, a certain direction, ching, you're done. Right? But a curved path, you got a lot of stuff to, you know, so you're going to need a lot more waypoints on the curve. You know, if it's a straight line segment, you just need the final and the initial. But a curved, you're going to need to do a lot more waypoints. So like 0.6 and 0.7 up here, for instance. So that's x6, comma y6 on graph paper, x7, comma y7 on graph paper. And then, so those are two waypoints, and then, you know, what you got to do is you got to get the distance between those babies. And they're not the only waypoints. You know, you might have a whole bunch. I'm just taking two at random here. I just kind of picked out two likely looking points. All right, so distance calculations. What do you think about? Well, distance, you should always think about Pythagorean theorem and the right triangle. So here's my little right triangle, and there it is. And I'm going to blow it up and put it down here, the big version, in the lower left, right above the origin here, this red. You know, that doesn't look very red to me. Does that look red to you guys? Yeah. All right. Maybe it's just the angle, I guess. Anyway, this red rectangle signifies the origin. Here's it actually is a little triangle up here on the path, but I blew it up and moved it down here. And okay, that's what you got to do. You got to try to get the hypotenuse. You know, that's the difference between, or that's the distance. The length of that hypotenuse is the distance between those 2 points. And then the other thing you have to do is get more time stamps or more time measurements at each waypoint. So, you know, you have T6 and T7, and that may be, you know, some certain time interval, some elapsed time delta T between those two. And if it's a curved path, there's a lot of other stuff that you have to specify. For instance, directions and speeds. Okay? And matter of fact, on a straight line path, you also have to define the speeds as well. All right? Carlos, that's you, right? And who was the other volunteer yesterday, Tuesday? Carlos and Erica. Okay, good. Carl, I'm learning names. Good. All right. And Malik, you're up here in the front. Good. We're sitting right next to Dare. And whenever you guys need help with something, come sit up front for a day or two with Darian or with the other TA if she's here. Definitely helpful. All right, so delta P excuse me, delta x and delta t. We need those for specifying, and we need a lot more of them if it's a curvaceous path. Another thing we need to do is figure out the direction of motion at each time. So let's go back up here to point 6 again. Go ahead and sketch an arrow that touches at point 6, point number 6, and give it an arrow shape, and that is what we call a vector, or the graph, the sketch of a vector that represents the velocity. In other words, the speed and the direction are represented by that arrow. Let's go to the next point and make yourself a bigger arrow. And this one's in a slightly different direction. The vectors, the velocity vectors, are always tangent to the path. If it's a curved path, it just gracefully touches at one point, the point in question on the path. So in this point, V7 just gracefully touches right here at point 7, right here, x7, comma, y7. And so some of the velocity vectors are, these two are kind of pointing up and to the right, so that's northeast, the northeast quadrant, if you will. And some of them down here, like this one at point 8, those are going to be pointing down to the southwest. All right. Now, I want you to look at my notes carefully. If you see where my cursor is, it says like V8. And look at the font for the V in V8. Can you see that it's a big, thick V, like a boldface? Okay, it's a different font that I use to indicate a vector. Now, if I have a diagram like this, I'll use a little teeny arrow over the top. All right, but I can't do arrows over the top inside these notes and stuff. I can only make little separate equations like this. So here's V8 with an arrow over the top. Here's V8 in the notes as a bold letter V. All right, so that's the two different ways that I do that. All right. The other thing you need to do to specify the motion on a curvaceous path is the speed at each time. And so you basically, if you did your reading in chapter 1, you know that you have to possibly take a lot of really fast measurements, like your speedometer does, and get a bunch of different times. So your speed at each time, V6 and V7, V8, might be a speedometer rating, but that's a speedometer rating is an average speed for a very, very small increment of distance, delta x, in your car, and a very small increment of distance, increment of time, delta t. And I don't know how fast a car does that, but I'm guessing maybe it's one turn of your front wheel or your back wheel or something like that. Does anybody know? Has anybody ever taken apart a speedometer on a car? Okay. Sometimes we get guys that know how to do that. Anyways, so you got to have speeds, you got to have directions, positions, and times, of course, as well. So now, vocabulary blurb in yellow. The word velocity is used to denote a physical quantity that encodes the speed and the direction of the motion of an object. And what we do is we use an arrow to draw it. And we can use other ways to write it in an equation. Boldface, like what I have here in item C, Roman numeral I and Roman numeral II. The arrow is to be longer or shorter depending on the speed. The direction of the arrow is to be northeast, north, northwest, west, southwest, south, southeast, east, depending on the direction. of motion. All right, so in this case, v7, the vector, is longer than v6, the vector. It signifies that the driver, or the object moving along this red curved path, he's going a little faster. He's got a higher speedometer rating there. All right. He's getting into the straightaway. And then down here, at V8, at point 8 here, he's in the middle of the straightaway, so he's still kind of cruising at high speed. But up here, going into the turn, whoa, he's got to ease off on the speed. So V6 is a little bit slower, a little bit longer of an arrow, a little bit shorter of an arrow. All right. So make a note of that about the word velocity. Now, when you're studying velocity, the one thing you don't want to do is be napping while I'm talking about it. Okay? So make sure that you're always awake and ready to think about everything that we talk about in this class. And in general, you need a position and a time, and you need a velocity. And for prediction, you need some way to express or generate the evolution of position and velocity over time. All right, so here's my, up here in the black text, position underlined, time underlined, velocity underlined. That's a full specification of the state of motion of this object at time t11, which is, I wrote down as 1:22 and 44 seconds p.m. All right, so that's the kind of thing. And these guys, we were just talking about that SpaceX rocket, and it was supposed to go off in space. And those guys, they got a bunch of PhDs trying to figure out, position, time, and speed and velocity for that rocket, because they want it to dock with the International Space Station. Or maybe they want to deliver something else into orbit. Okay, and you just don't want to just throw. Space is big. It's bigger than the surface of the Earth by definition because it's out farther. Okay, so it's a big place. You got to know where you're going, and it's got to be really precise. But this is basically the thing that their computers are trying to spit out in a reliable manner, and Galileo's the one that figured out how to do that. All right, so here's vector V11 drawn in as an arrow, whatever it happens to be. Last time we finished by looking and doing some sketching. Raise your hand if you downloaded the talking PDF. Oh, 2 people. Oh my goodness. It was? Ooh. Okay. I'll put it on the front, a link to the Talking PDFs page. Okay. I'm not mad at you guys anymore. I was mad for a little bit, but now I'm cooled off. Okay. All right. So here's what the PDF looks like, and this is just what we sketched. And you can hear me blabbing. Did you guys listen to it? Figured out how to listen? It worked okay? Yeah, it's nice. Now, in this particular motion, constant velocity, and we dreamed up, 2.4 meters per second or something like that, 2.5. The time evolution equation is simply delta x equals v delta t. If you know the elapsed time, delta t, and you know the speed, you can figure out the change in the position. Ding! So you know the time, you know the new position, and you know the speed because it's a constant value. So the speed doesn't evolve, only the position evolves. All right, so this is what you would call the time evolution equation. Here's a similar graph for the afternoon, the noon lecture. We use a slightly different set of numbers. But this is the velocity, or this is what we would call the distance rectangle. two different different distance rectangles. And for this one, the time evolution equation is delta x equals v delta t. Now, where we finished in the morning lecture was with this one. We were talking about something that's in free fall and that drops for a certain amount of time. And the time evolution equation for this accelerating system, something for which the velocity is changing. It's not a horizontal line on the velocity versus time graph. It's a slanted line. Free fall, it changes gradual. Well, it's not gradual. It changes quite a bit, but it changes uniformly over time. And when we study this triangle, it is going to give us the time evolution equation for accelerations in general and for free fall in particular. So let's start talking about Galileo's free fall activity. And hey, would you guys like to dismiss early? I mean, I think we're going to. Raise your hand if you feel like dismissing early today. Okay. And then you could go home and get a little extra shut-eye if you want. Okay. And anybody, if you're against dismissing early, I'll stay here and talk with you. But let's talk about Galileo. Famous, famous, famous. Now, nobody knows if he actually did this. He went, the legend is that he went to the top of the Leaning Tower of Pisa and he dropped a cannonball and then he dropped a musket shot, so a little bit smaller lead ball, from a musket at the same time. And some people, his lab assistant, who became a scientist himself, said, yeah, he did it. And other people said, no, he didn't really do it. He just thought about it. He just, made it up. But this is what he wrote about it. This is a quote from Galileo. So you can make a note of this. I observe a stone initially at rest, falling from an elevated position and continually acquiring new increments of speed. All right. That means that it's getting more and more downward speed. All right. And although this is a stone, and he doesn't mention the Leaning Tower of Pisa, he did write this. Okay? And so let's take a look at this. Here's another quote from Galileo. If we now examine the matter carefully, we find no addition or increment more simple than that which repeats itself always in the same manner. The increment repeats itself always in the same manner. Repetition. So every second of free fall, you get the same. Whoa. Ooh, you know what? We have to start using the HDMI cable. Dude, we forgot to take this out last time. Wow, it's still here. Good. Because it doesn't flicker like this VGA converter.
The HDMI port's on the other side.
I know it is. Yeah. But we got to start doing. We did it. Caroline and I did it. Yeah. All right. Sorry, just a little chat with my TA. So the idea for free fall, which Galileo figured out, is that every second of free fall you get the same amount of downward velocity in addition to what you already had. All right. So you acquire the same amount in every second. So here's how it would look. Okay, let's say that he drops the bowling ball or the cannonball and then starts a stopwatch. Now, he didn't have a stopwatch, but he had ways of measuring the time. He invented a water clock. It's kind of cool. I don't know if he had one for the Leaning Tower of Pisa, but let's just say that he had a stopwatch. So at time t equals 0, the speed is 0.00. In other words, it's at rest. Okay? So he said, I'll drop it from rest and start my stopwatch. Okay? And then after 1 second, this is what the speed would be. And this is accurate. And he didn't have the meter system. They used cubits or feet or something like that. They probably did use seconds of time, but not meters. Anyways, 9.8 meters per second of downward speed. And that's what happens on Earth. The force of gravity gives everybody equal increments of speed for every second of free fall. So in the next second, he gets another 9.8. Total, 19.6 meters per second downward. And Erica, that corresponds to the fact that when I release it, it's the dollar bill's at zero, it's at rest, but it's going faster by the time it gets to your hand. Okay? After 3 seconds, ching, another 9.8. Total, 29.4. 4 seconds of free fall, ching, another 9.8. So basically it's 9.8 times t, whatever t is. I mean, if you start from 0, it's 9.8 times t, or 9.8 times delta t. So write down etc. And make a note that the speed is actually a downward speed. And if we were going to be, if we were going to get fancy, we would actually put minus signs on it, and then that would be unambiguous. But if you want to use positive numbers, as we have done, you have to add the word downward, which we've done at the bottom of the table. All right? And the increase repeats itself. The increase in downward speed. Always another 9.8 meters per second of downward speed for every second of free fall. Now, in a tenth of a second of free fall, you get a tenth of 9.8. What's a tenth of 9.8? That would be 0.98. Okay, in a tenth of a second. So if you're thinking about a tenth of a second, every tenth of a second, another 0.98. So you go 0.98, 1.96 for another tenth of a second, and so on. If you're thinking in terms of minutes, it'd be 60 times 9.8 per minute. It's good. I got it. You got it. Okay. All right. So free fall acceleration. That's a table for it. Here's another way to write it. And we usually use the symbol G to express the free fall acceleration on the surface of Earth. 9.8 meters per second per second. All right. That's the increment. 9.8 meters per second of speed for every second. So it's actually meters per second, or if you want to write it in a more compact notation, 9.8 meters per second squared. Those are both kosher ways. And sometimes when I'm writing a test and I don't want to use exponents, I'm trying to write it fast and trying to keep it compact, I'll go 9.8 meters per second. But otherwise, sometimes I'll use meters per second squared. Now, in general, the formula for acceleration is the change in the velocity, delta v, divided by the change in the time. So from time 0 to time what have you, you have an increase in downward speed. So from time 0 to time t equals 4 seconds, you have 4 times the 9.8 meters per second. Question.
What exactly does A stand for again?
Acceleration. G stands for the acceleration due to gravity. Okay? So we use the acceleration due to gravity so much we give it its own symbol. Kind of like, the ratio of a circle's circumference to its diameter. It's got its own symbol, known as pi. Okay? So some numbers, we use them a lot. We just give them their own symbol. Or let's think of a number that's got its own symbol. Pi. E. For those of you that have had calculus, the E, the natural base. There's bunches of them. Anyways, G's is what we have. And so let's get back to the distance triangle. We sketched it out last time. Let's get down to the nitty gritty. All right, here's 4 seconds from the top of a really big tower. The Leaning Tower of Pisa is not this tall. It would probably take a second, 1 point something seconds. You know, just same way with the like the UCF library, probably close to 1 second, maybe a little bit more, maybe a little bit less, to fall from the top of the library if you drop it. Now, we're going to use the triangle formula, 1/2 base times height, but first let's set it up. Okay, so the first dot here, actually the first dot is right here at the origin, 0, 0. Okay, you're starting from rest, right? And then after 1 second, now on this one, I am using negative signs on this graph. This negative 9.8 on this table, or excuse me, on this graph means downward, okay? And so here's the second dot, negative 9.8, and then 1 second across. Now for reference, I put the 5-second mark out here. So there's 5 seconds here, 4, 3, 2, 1. But I didn't put the first 4 numerals of the time scale because I didn't want the picture to be too crowded and cramped, that's all. But these are my drop speeds, or my drop velocities actually, because they have a minus sign. Second, all right, another 9.8 negatory. Total, negative 19.6. All right? So when you're graphing this out, just draw a straight line and put the dots, you know, kind of equally spaced as well as you can, and kind of eyeball this in. And I did it really carefully, really precisely. Okay, so this is accurate. If you want to go and get some graph paper, yeah, you can do it on graph paper, or if on a spreadsheet or something like that. After 3 seconds, the 4th dot in the series, let's see, 9.8 times 3 is 29.4, and it's negative, so it's negative 29.4. And then negative 9.8 times 4 is 39.2. So here's the last one. All right, and that's where my table for the Leaning Tower of Pisa slide finishes. Now, here's the area that we want to interpret. Go ahead and draw your triangle in there. The area of this polygon that happens to be above the velocity graph and below the time axis, that represents the distance that this object has dropped. All right? Now, the vertical size of this, you know, to get the area of a triangle, it's 1/2 base times height. Okay, so the height of this is just g times delta t. G times 4 seconds. All right? And the width of it up here, 1/2 base times width, that's just delta t. There's no problem there. We're looking good. All right? Now, so now if you go 1/2 times the base, delta t, times the height, g delta t, then you get this equation. And on this version, I left out the delta. I wrote it as 1/2 g t squared. And I did a little bit of rearranging. I put all the delta t's in one term here. So that's if I really did it consistently, this would be delta t quantity squared. But this is the way that we normally write it. For a certain amount of time t of free fall, this is the drop distance. And students, this is the drop distance formula. D equals 1/2 gt squared. Now, if you're up on top of the library and you're dropping water balloons or something from the top of the library, you would use this one, this formula that tells you the drop distance. So you drop it and you time it, and then when you hear it splat, you stop your stopwatch, and then that tells you the height of the library. Then you do this equation that tells you the height of the library, the drop distance. But if you throw it, you can't use this one. You got to use a different formula, and we'll get to that on Tuesday. But for us, 1/2 GT squared, yeah, good. If you throw it upwards, and then it comes back down and hits the sidewalk below you, you got to use a different formula. But this one is just the drop distance. So you drop it, and it goes down and impacts. So it's free fall from rest. Now, get your clickers ready. We're going to do a clicker question together. Let me do a different question here. All right. We're going to do a problem from this movie, The Fellowship of the Ring. We're going to drop a rock down a well, and let's say that we hear the splash after 3.2 seconds. So how deep is the well? So go ahead and write that down. And then here's Peregrine Took, about to get in trouble. But let's use this formula here. Go ahead and calculate and type in the distance. Okay, I'm starting, the question is started. Calculate it, 3.2 seconds of free fall, and G is 9.8. And then type in your answer. And can you help Malik with his calculation? And let me turn the lights up so you have some light. Okay, 3.2 seconds of free fall. How far down into the mines of Moria does it go? Malik, you're lefty. God made a few perfect people. Everybody else is right-handed. Did you ever hear that one? It's a good one. All right, yeah. As many as you want. This on iClicker doesn't matter, but give me 2 decimal points. So that's the nearest 0.01 meters. That'll be sufficient. Let me see, 3.2. That's about 9 point. Yes.
Will it always be 9.8?
For G, yep.
Yes.
Oh, and that brings up a good point. We'll talk about that when we finish this question. Will it always be 9.8? The answer for free fall is yes, unless you're on the moon. Did you ever see those? What's your name? Shiraz. Did you ever see those videos of like the Apollo astronauts on the moon, and they're jumping around? They could really jump. And did you ever see those? That's because gravity is so much weaker on the moon. The moon is so much smaller. Gravitational acceleration is 1/6 of 9.8. And so up there, free fall is a lot pokier. But for here on Earth, yep, anywhere you go, 9.8. Question?
Is it 9.8 meters per second squared?
Yeah, 9.8 meters per second squared. Question? Yeah. What? When you're done with your number, hit the send key. Yeah. And you should get a check mark. Did you get a check? Yeah. If I'm asking you a y coordinate. So if I'm just asking you a drop distance, You know, how deep is it? You don't say, well, it's negative 40 meters deep. You just say it's 40 meters deep. But if I ask you, well, what is its position on graph paper? Then you might need to use minus signs for something that's falling. 2 decimal points. Okay. Yeah, distance can't be negative. So if I ask a distance, it's always a positive number.
Like, would you use feet, meters, like,
Feet and meters.
yeah, like, to the answer, like, for basis, like, is there a certain measurement you have to go over? For the end, like,
Oh, you mean at the a symbol? No, just the numeric part, just the number. All right, I see 154. Okay, 15 seconds to type in your answer. Malik, you got yours in? Good. Did it help? Having the brain with? That's right. Yeah, and you can sit up here every day, any day you want. It's fine. It's good. She really helps out. She's very nice. And see, eventually, Malik, you're going to be so up to speed that you're going to be sitting in the back and you're going to be helping everybody sitting around you. It's inevitable. 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for here. Oh my, what? What is this? I see a lot of 50.18, 50.176, 50.2. Let's investigate this. All right, so here's your calculation. And so if you want, just go ahead and jot this down. Okay, 1/2 GT squared. Here's the 1/2, 0.5. And here's the 9.8 meters per second squared. And 3.2 seconds. Now notice that's quantity squared. And I want to make a point here that a student asked about. Is it always 9.8 meters per second squared? And the answer to that is yes. If you're on the surface of Earth, from the top of Mount Everest to the bottom of the Mariana Trench in the Pacific Ocean, or anywhere in between, the freefall acceleration is 9.8 meters per second squared. Now, if you're far out in space, you know, like the where the space station is or the shuttle, if you were to bail out of the space shuttle and go into freefall, which would be kind of cool to do, except you wouldn't survive it. But well, that would be really cool. Can you imagine? I mean, if you had like a fireproof suit that you could, you know, like an Iron Man suit that you could do it in, that'd be cool. But anyways, the free fall acceleration out that far is a little bit less. The further away from Earth you go, of course, the smaller it is. All right, here we go. And what I did here is 0.5 times 9.8 meters per second squared. That's 4.9. And then the other thing I did was I computed 3.2 seconds quantity squared. Now notice how I've written that. 10.24 for the numeric part. And then inside the square brackets, I have seconds to the second power. Okay? So when you square that, you have to square both items inside the square brackets. So the square of the numeric part is 10.24. The square of the seconds is second squared. Now that second squared up here cancels this one down here in the parentheses, 4.9 meters per second squared. Okay, that second squared in there cancels the second squared in the square brackets. Right? So you're left with meters. And that's what you want for a distance. Now you multiply the 4.9 and the 10.24. And there we go. So I have it written down for 3 decimal points. 50. So depending on what I ask you, I mean, if this were a homework, oh, by the way, it is in the homework. You are going to do this. So you will have some chances to do the Mines of Moria calculation and a few other brain burners on the homework. This one's pretty deep. Now, raise your hand if you don't have classes on Friday. Ooh. Okay, raise your hand if this is your last class of the week. You're dismissed. See you, and homework 2 is running. See you next week. Early dismissal today.